Good afternoon, students. Let us have a brief revision of whatever we have been discussing in the previous class. We have been discussing the cyclic codes, and in the cyclic codes we have been discussing about non-systematic code vectors and the systematic code vectors. And we had seen how to multiply the generator polynomial with the data vector to obtain the code vector. But that particular method resulted in the non-systematic code vectors, which means the check bits were not distinguishable in the code vector. Neither the data bits were not distinguishable. Later on, we moved on to the systematic form. And in the systematic form, we had a procedure of polynomial division where we used to find out the remainder of the particular division, and then the remainder was used along with the data vector for obtaining a code vector. That was the exercise which we were seeing in the last class. Finally, the remainder and the data vector were concatenated to obtain the code vector. Let me show you that exercise once again, because in the last class I did not completely show you the table. Even though I showed you the table, I did not discuss it fully at the end. So, find all the code vectors in the systematic form for the previous exercise was the present exercise. So, in the systematic form of cyclic codes, the check bits come at the beginning of the code vector, unlike the block codes where we had the check bits at the end. So, we arrange it like this: check bits in the beginning, n minus k check bits, and message bits k. The check bits are generated using the remainder polynomial r of x, which is obtained in this manner: x power n minus k into d of x divided by g of x plus q of x, where q of x is the quotient polynomial and g of x is the generator polynomial, d of x is the polynomial corresponding to the data vector. Where r of x should be represented in the degree of n minus k minus 1. I had some confusion in the last class about this. Today I am going to discuss in detail when I show you the table. Here I have written it as n minus k minus 1. Later on I have written as n minus k. That was the confusion. But when we have a 7,3 code, the remainder polynomial has to be written in the degree of 4. Means it has to be n minus k. Why have I written n minus k minus 1 here is because we have the first term in the polynomial is 1 itself, 1 plus x square plus x cube, that way it goes on. That is why I had written it here. But ultimately the degree is not n minus k minus 1. Degree is n minus k minus 1. If it is 7,3 code, then the remainder polynomial will have 4 terms there. So it must be 1 plus x square plus x cube. So degree is n minus k minus 1. Total number of terms will be 4 there. They have to be represented in terms of 4 only, even though we do not get all the 4 terms there. I will tell you about it later on when I show you the table. So in this particular case, x power n minus k is x power 4. So the code vectors are computed and tabulated as follows. When d of x is 0, 0, 0, obviously v of x is all zeros. For 0, 0, 1, we had performed this division, right? For 0, 0, 1, x power 4 into x squared, you can see this, x power n minus k into d of x. So for 0, 0, 1, it is 1 plus x squared, but the first 2 terms are 0. So the last one is x squared itself. So we get the term here x power 6. Now x power 6 has to be divided by the generator polynomial, and then the remainder polynomial has to be obtained. Now expression for the remainder polynomial is this. But for obtaining the remainder polynomial, we will have to perform this division. The quotient polynomial may not be important for us at all. Let us see that later on. Just for the sake of accuracy, I have written this equation here now. But the quotient polynomial we may not be using at all. Now for 0, 0, 1, it is x power 4 into x square is x power 6. Now x power 6 is divided by the g of x. G of x given is 1 plus x square plus x power 4. So we get the remainder polynomial as 1 plus x cubed. Now this can be written as 0, 0, 0, 1. Sorry, this can be written as 1, 1, 0, 1. Because this 1 is present, x is present, x square is not present, x cubed is present. So it is 1, 1, 0, 1. That way this remainder polynomial can be represented. In the same manner, for all other data vectors, we will obtain the numerator, and numerator is divided by the denominator. Denominator is g of x, which is going to remain the same always for all these computations. So here for 0, 1, 0, we get the remainder as x plus x square plus s cube. So we can write it as 0, 1, 1, 1. That is because the very first term 1 is not present here. So it can be 0, 1, 1, 1. So the degree of the polynomial must be n minus k minus 1. That is what I had written there. But the number of terms must be 4 actually. Even when we write the r of x, we cannot leave out this. We will have to add that 0 here. For all other 3 terms, we can put 1, 1, 1. So in the same fashion, as I had explained in the last class, we are going to find out the remainder polynomial for every data vector, which I am showing you here. This I had already shown you in the last class. That's why I am going faster. Now lastly, for 1, 1, 1, we have the remainder polynomial as x. So corresponding to 1, 1, 1, the remainder vector is now 0, 1, 0, 0. Because only x is present, other 3 terms are absent. So it has to be 0, 1, 0, 0. So finally, the systematic cyclic code vector c of x is written as r of x and then concatenated with d of x. I cannot say concatenation also, because it is not a logical operation at all. Just for the sake of telling, I am telling it as concatenation. Otherwise, we are writing them adjacent to each other. That's all. And the results are tabulated now as follows. You can see here, for message 0, 0, 0, obviously code vector is all 0, 0. And for 0, 0, 1, message was x squared, and the remainder polynomial which we obtained was 1 plus x cubed. Now the remainder polynomial is written in the beginning, and the data vector is written at the end. So corresponding to 1 plus x cube, it is 1, 1, then 0, then 1. That is there here. 1, x, then here you have x cube. In between x square is absent, so in that place write 0. Now why I had mentioned that we have to have a total degree of the remainder polynomial fully written. Answer is, let me annotate here. So Ankit has given the answer 0, 1, 1, 1. Fine. Now, in this particular case, 1 plus x square, you can see 1 is present, x square is present, x is not present, x cube is not present. So, here 1 and here it is x square. But x is not present, we have to write 0. X cube is not present, we have to write 0. Ultimately, it has to be 4 bits only. Similarly, for this x, you can see 1 is not there, x square is not there, x cube is not there. Still, we have to write 4 positions here. We have to write 4 binary digits here, because ultimately our code vector has to be 7 bits. So data vector is 3 bits. Ultimately, we should have 4 remainder polynomial bits. That is why I had told that it has to be expressed in the degree of n minus k minus 1. So that way, for all the data vectors, we have obtained the remainder polynomial. Accordingly, we are writing all the remainder polynomial first, then we are writing the data vectors next. This way, we have the code vector. Now you can see all of these code vectors are systematic, because we are writing the remainder polynomial in the beginning and we are writing the data vector at the end. They are easily distinguishable that way. So we have obtained the systematic cyclic codes now. in contrast with the earlier method where we had non-systematic cyclic codes. So please remember, for obtaining the non-systematic cyclic codes, multiplication is enough. Multiplication of the polynomial vectors is enough. But for obtaining systematic cyclic codes, we have to find out the remainder polynomial. Here the procedure is slightly tedious. Compared to the earlier procedure, this is slightly tedious. But that is the price we have to pay for obtaining a systematic code vector. Always when it is a systematic code vector, even at the receiver, it is easy for the receiver to distinguish which are the check bits and which are the data bits. If they are mixed up, then the receiver will have to have a lot of computational work. So that way systematic code vectors are always better when compared to non-systematic code vectors. Of course, they have their own advantages, they have their own disadvantages. If you go for non-systematic code vectors, even the errors can be distributed randomly because the check bits and data bits are not distinguishable that way. That is the advantage there. But the disadvantage is we will have to work a lot for recovering back the corrected data vector. So now in this table, it can be observed that all the code words are cyclic and unique. I had shown you earlier also. Let me show you here. 1101,001. Now you can go for a rotation here. When you go for a rotation, it will become 111,0100. 111,0100 is here. So that way a rotation always results in another code vector. That means they are all cyclic, and you can see they are all unique. Means there is no code vector which is same as the other code vector. That way they are all unique. You can also see that they are linear. That property is also there. Linear means what? If two code vectors are added, it will result in another code vector. That I will tell you later on after I tell you this note. The cyclic codes are linear codes as well. That is, the addition of two codes yields another code present in the code set. Let us see that. Let us add this with this. The second code with the third code. Now it is 1, 1, 0. Then it is 0. Then it is 0. Then it is 1. Then it is 0. Carry can be discarded. So you can see this with this. Let me write 1 plus 0 is 1. Let me write it using my right hand. I have been using left hand for the movement of mouse because due to the continuous clicking of the mouse, I have problems with my right hand's finger. That is the outcome I got in this online sessions. Right from April onwards, we have been using only laptop and mouse continuously. Due to the continuous clicking of the mouse, I have problem with my right hand's forefinger. And due to the continuous looking at the mobile phone and the laptop, even my eyesight has problem. But we have to live with this problem. We don't know how long, but that is part of our life now. Anyway, if I tell my problem that is of no use for you, you will say you also have enough problems, right? So let us add these two. Now this is 1, 1, 0, then 1 plus 1 is 0, then carry forward here 1 plus 1 again 0, carry forward here 1 plus 1 plus 1, so that is 1, then 1 plus 1 is 0, last one can be discarded, that is the overflow or the carry. Now 0 1 0 0 0 1 1 0 1 0 0 0 1 1. Is it there anywhere? Zero 1 0 0 0 1 1. Is it there anywhere? No, it is not there, right? Does the rotation of anything else becomes that? No, because in this particular code set, we have all 4 ones and 3 zeros. The answer which I have obtained is 4 zeros and 3 ones. So that way this is not there present. That means this particular addition is not giving us a result. Let us add some other code now. Let us see, just for the sake of curiosity. Let us add this with this. Now 0, 1 is 1, 1, 1 is 0. Now there is a carry here, 1, 1, 1, that is 1. 1 is a carry here, so this is 0. Next carry comes here, 1. Here it is 1. Here it is 1. So 1, 1, 1, 0, 1, 0, 1. 1, 1, 1, 0, 1, 0, 1. Is it present anywhere? No. Again, this is having 5 ones and 2 zeros. Actually, our addition should contain only 3 zeros and 4 ones. So that is not getting resulted here. Is it normal addition or modulo 2 addition? Oh yeah, Kuldeep. Thanks for reminding me. Let us go for modulo 2 addition. I had totally forgotten. Okay. Let us perform modulo 2 addition only. Let us say we will add this. 0, 1 is 1, 1, 1 is 0, 1, 1 is 0, 1, 0 is 1, then 0, then 1, then 1. So 1, 1, 0, 1, 0, 0, 1. 1, 1, 0, 1, 0, 0, 1. It is here. Correct. So we got this. I had totally forgotten that it is a modulo 2 addition. Thanks, Kuldeep, once again. So the addition of these two codes is resulting in the third code. Let us try the very first example itself now. This one and this one let us add. So 1, 0, 1, 0, 1, 1. Then it is 0. 1, 1 is 0. And 0, 1, 1. 1, 1 is 0. 1, 0 is 1. 1, 0, 1, 0. 1, 0, 1, 0, 0, 1, 1. I had written 0 slightly differently here because I am using the mouse only. 1, 0, 1, 0, 1, 0, 0, 1, 1. It is here. 1, 0, 1, 0, 0, 1, 1 is here. That means the modulo 2 addition of any two code words is going to result in another code present in the code set. That way, these are all linear codes. So we had discussed the block codes as linear codes earlier. Now we are discussing the cyclic codes also as linear codes. Now, the second one note is for obtaining systematic cyclic code, R of x has to be obtained and then it has to be represented in the degree of n minus k. So this sentence is correct according to me. Degree must be, no, again, whatever I had written earlier itself is correct. Degree must be n minus k minus 1. Total number of terms must be n minus k. So represented with the terms, I should change this now. Instead of the degree, this is now the number of terms in the remainder polynomial. Degree is 1 plus x square plus x cube. That becomes n minus k minus 1 only. So while writing notes, I might have been doing the oversight when I wrote degree here. This is not a degree, this is the number of terms. So then the code vector is written as c of x equals r of x along with d of x. This is equivalent to c of x equals r of x XORed with x power n minus k into d of x. That is what we had done, right? When we did that polynomial division. So this is equivalent to the modulo 2 addition of r of x with x power n minus k into d of x. Let us see what are the properties of the generator polynomial. So just like in the linear block codes, intelligence was present in the parity check matrix there. We had a parity check matrix called P, which was derived from the Hamming matrix that way. We had a parity matrix, we had a parity check matrix. Actually, parity check matrix itself was called as Hamming matrix also, to honor the scientist Hamming. Now the intelligence was present in that parity check matrix only. Now in the case of cyclic codes, the intelligence is present in the choice of the generator polynomial. In all our previous examples, generator polynomial was given. Now using that we had constructed the cyclic codes. Please recall that in the module 4, we had that parity matrix given. Now using the parity matrix, we had generated the other code words. But later on, we had seen how to actually frame a parity matrix also. We had seen what all rows parity matrix cannot contain. That also we had seen. The identity element should not be there in the parity matrix, and obviously the 0, 0, 0 term should not be present in the parity matrix. Those things we had seen in module 4. Now similarly, in the case of cyclic codes also, even though till now generator polynomial is given, it is we who are going to decide what must be the type of the generator polynomial and in what way the generator polynomial has to be intelligent. Hence, g of x has to be chosen based on some properties. Let us see those properties now. If g of x is a polynomial of degree n minus k, and if it is a factor of x power n plus 1, then g of x generates n comma k cyclic code. Now this is the requirement. The requirement is g of x has to be a factor of x power n plus 1. That is how we have to choose. We can't randomly choose any generator polynomial. Please recall in module 4, we could not randomly choose one parity matrix also. We had those Hamming bound conditions also there. In the same way, here also, we cannot randomly choose any generator polynomial. It has to be a factor of x power n plus 1. Then g of x generates n comma k cyclic code. This is the first property. Please remember this property because this is going to be important later on when we discuss the other properties. So g of x has to be a factor of x power n plus 1, first property. Let us see an example. X power 7 plus 1. Let us say we want to have a 7 comma 3 code. Now n is 7 there. Or we can have a 7 comma 4 code. In both the cases n is 7 there. So when n is 7, x power 7 plus 1 is now x cubed plus x plus 1 into x power 4 plus x square plus x plus 1. This is again a modulo 2 multiplication. Remember that. Modulo 2 multiplication. So if you can factorize x power n plus 1, now the factors of x power n plus 1 can be used as generator polynomials. So here, if g of x is 1 plus x cubed, then 7 comma 4 cyclic code can be generated. And if g of x is 1 plus x square plus x power 4, then 7 comma 3 cyclic code can be generated. You can see both of them. So you have this and then you have this. Here you have x cubed and here you have x power 4. Now if we choose this 1 plus x cubed, then we can have 7 comma 4 cyclic code. You can see this. Here it is n k, here it is n minus k minus 1. You can see this. N and k, sorry, n minus k, not n minus k minus 1, n minus k only. 7 and 4, n minus k is 3. Similarly, if we choose g of x as 1 plus x square plus x power 4, then it can be 7 comma 3. Why? Here you can see again n minus k. 7 minus 3 is 4. So this way, any factor of x power n plus 1 can be used as a generator polynomial. So for generating a 9 comma 4 cyclic code, g of x has to be the factor of x power 9 plus 1 for generating a 9 comma 4 cyclic code. And g of x has to be of the degree 5. Why 9 minus 4 is 5. So g of x should have that particular degree because we have to divide, we have to multiply based on our requirement of whether it is a systematic cyclic code or a non-systematic cyclic code. So this is the first property. G of x has to be a factor of x power n plus 1. Now let us say the second property. When g of x is a factor of x power n plus 1, then x power n plus 1 is equal to g of x into h of x. Now we had seen two factors there. Now one of them, if it is taken as g of x, the other one can be now h of x, where h of x is called as the parity check polynomial now. Now you can see here g of x has to be the degree of n minus k and h of x has to be the degree of k. We had seen that x power 7 plus 1 is 1 plus x cubed into 1 plus x squared plus x power 4. Now for generating a 7, 4 cyclic code, 1 plus x cubed has to be taken as g of x. And now 1 plus x squared plus x power 4 will be h of x as it is of the degree 4. Which means what? Which means at the transmitter for generation this can be used 1 plus x cubed, which is a g of x. Now at the receiver this can be used 1 plus x squared plus x power 4 can be used as h of x here. Now just like we had a parity check matrix earlier, we can have a parity check polynomial at the receiver. Now you can see that both of them are factors of x power n plus 1. Now conversely, for generating a 7, 3 cyclic code, if 1 plus x cubed is used as h of x at the receiver, 1 plus x squared plus x power 4 will be used as g of x at the transmitter. We can make any particular choice, but that is dependent on n, k, right? That is how we have to choose the polynomials. So that is why I told that x power n plus 1 term is going to become important for us for choosing the generator polynomials and the parity check polynomials. Both must be the factor of x power n plus 1. Let me proceed. Now the third property is the polynomial x power n plus 1 will have both g of x and h of x as its factors, right? See, 1 plus x cubed and 1 plus x squared plus x power 4 are both factors. So if you use x cubed plus x plus 1 to divide x power 7 plus 1, you will get the other one. That means if you use g of x, then the other one is h of x. Now when you use h of x, the other one is g of x. So that way, when you keep on dividing, you will get the remainder polynomial 0. That is the requirement. Remainder is 0. So we have seen these three. Even though it is actually one property, we have seen this property with the three parts. G of x and h of x both must be a factor of x power n plus 1. And we have both now. We have a generator polynomial also. We have a parity check polynomial also. Now you may wonder, why are we discussing again generator and parity check matrices? The reason is there. The reason is there now. We thought to go away or get away with the matrix computations, we are going for cyclic codes. That is why we thought we are using polynomials where our task is going to be easier. But why are we discussing again matrices here? In Kannada we have a proverb called Hodya Pishache andre bande gavakshili anta. Somebody is telling the ghost, if the ghost has gone out of the house through the door, when he closes the door, then he happily says, oh, the ghost, you have gone out. Now the ghost says, your upper window is open. In Kannada we call it as gavakshi. In English, what do we call, I don't know. And through that, the ghost says, I have come back through the upper window. It is actually a ventilator window. I think gavakshi is called as ventilator window in English. So same way, in the fourth module, we had worked with all these matrices. And we went to discuss the cyclic codes with the purpose of getting away with the matrix calculations which were cumbersome. Now, why are we discussing matrices once again? There is the reason. The reason is again the same. Let us see the reason. The process of generating the systematic cyclic codes is quite cumbersome. Why? We have to go for polynomial division, which is quite cumbersome. We had gone through that polynomial division for obtaining all the code vectors for the given data vectors. For each one we had to perform the polynomial division. Even though quotient was not useful, remainder was useful for our generation of systematic cyclic codes. But that is quite cumbersome, as is evident in the previous exercise. Now, to reduce the computational efforts of this polynomial division, the same code vectors can be generated using the generator matrix G. So, I am repeating the Kannada proverb, Podya Pishache andre bandre gavakshili, means generator matrix has come back now here. Let us not call it as Pishache now, right? It is not a ghost. That proverb is telling that way. But matrix is a highly useful mathematical element. I don't know who invented matrix. I keep on telling that whoever invented matrix is a genius in the mathematical domain, and whoever invented operational amplifier is a genius in the electronics domain. Both are wonderful that way. But both are very difficult to understand that way, right? With the matrix multiplication, if you remember your matrix algebra, cofactors, adjoints, so many things you will remember. But matrix is a very beautiful element in mathematics. There is a upper level approach of same matrix algebra in another course called linear algebra, where matrices are extensively used in the course called linear algebra. So, the matrix has come back now. Let us not consider it as our ghost. Let us consider it as our friend. So, why the matrix came back now? Just to avoid the continuous division of polynomials, which was cumbersome. So, the same code vectors can be generated using the generator matrix G. Let us see how to write this generator matrix G now. As we already know, the generator matrix G is of the order K cross N. We had seen it in the last module. Now, this matrix can be obtained by using G of x and its products as follows. Now, once we decide upon the generator polynomial G of x, we can have a generator matrix, which I will be showing you now. As C of x is obtained, that means the code vector is obtained using the remainder polynomial and the generator polynomial, all the code polynomials are divisible by G of x now. Right? See, we obtained a remainder polynomial by a division, and remainder polynomial was concatenated, so to say, with G of x. And we had a quotient polynomial also. But you can see the code polynomials are divisible by the generator polynomial. How come? All the generator polynomials are the factor of x power n plus 1. That way they are all related. Again, as I have been telling you many times in the previous classes, the proof for all these statements is beyond our curriculum. Just like we had discussed earlier that even though we deal with the binary algebra only with 0 and 1, I have been telling you that it has many such strange properties which we had seen in the previous module. In the same way, when we represent the same 0 and 1 even in the polynomial fashion, using this modulo 2 algebra again we will have all these strange properties. Of course, they are not strange properties, they are regular properties, but we did not know that Boolean algebra would yield so many such properties later on to be applicable to the technology. Of course, that is the beauty of nature anyhow. Even though many times we see something in nature as very simple, when we try to understand that very simple thing, that becomes really a very complicated thing. In the garden, when you see a small flower, you will feel as if it's a simple flower. According to you, a flower is a flower is a flower, that's all. What is so great about the flower? But you think or observe deeply about the flower, how come the flower got that particular shape, particular size, particular beauty, particular color, particular fragrance, particular arrangement of pollen grains? How come ultimately the plant's roots are in earth? Plant is only absorbing nutrients from earth. It is only an interaction of photosynthesis happening, sunlight, and then water molecules and the nutrients from earth. Now, whatever you thought as a very simple thing is no more a simple thing. Which means, whatever you thought as a flower as a very simple thing, the flower is the very complicated thing now. How come the flower came into existence on top of a plant, where the plant didn't have all that intelligence or consciousness to manufacture the flower on its body? That is God's wonder. Same way, in the binary algebra, even though we are simply using the 0 and 1, only 2 bits we are using. Now, just because of these 2 bits, what all types of applications we are going to have, that is wonderful that way. Again, for many of such things, the proof is beyond our comprehension, isn't it? Now, for the proof of the origination of the flower on the surface of the plant, is it under our comprehension so easily? We can simply wonder at the creation of God or creation of nature, because nature is God, God is nature, nothing else. Now that way we can say nature is conscious, nature is intelligent, but mud is not intelligent, water is not intelligent, sunlight is not intelligent, air is not intelligent. They are all material forms. Still we see a life form where we see a beautiful flower on the surface of a plant, on the body of a plant. You should check for one particular flower that is called Krishna Kamala in Sanskrita. That is called passion flower in English. Just Google for this passion flower in English, you will really understand the sentence which I told you now. Okay, same way when we use binary algebra, we think it is simply 2 binary digits 0 and 1. And when we as hardware engineers, when we think, we will think this 0 and 1 is nothing but switching on of the transistor, switching off the transistor, that's all. When the transistor is under saturation region, its collector, if I consider BJT as an example, the BJT's collector will be at 0 volts, so we will take it as 0. When the BJT is off, the collector is at VCC, so we will take it as 1. We simply think that way. But ultimately, it is connected to some strange properties that way. So let me come back without deviating further, discussing other things. C of x is obtained by using R of x and G of x. All the code polynomials are divisible by G of x. This means that G of x is a factor of all the code vector polynomials. Now, just like G of x, the products x into G of x, x squared into G of x, x cubed into G of x, and so on up to x power k minus 1 into G of x also represent the code vector polynomials. Now, that is where the secret is. Code vector and generator polynomial are anyhow related. Now, the products such as x into G of x, x squared into G of x, x cubed into G of x, so on up to x power k minus 1 into G of x, these also represent the code vector polynomials. Now, these products can be used to construct the generator matrix in the order of k cross n. That is the outcome of this discussion now. Just like we had that factor x power n plus 1, by using the factors of x power 1 plus 1, n plus 1, we had g of x and h of x. Now, to avoid the polynomial division, we want to have a generator matrix. Now we want to populate the generator matrix with the elements, right? Now what should be the elements in the generator matrix? Just like the way in which we had discussed in the previous module, what should be the elements in the parity matrix? Now here, what should be elements in the generator matrix? So the products x into g of x, x squared into g of x, x cubed into g of x, that way it can go on. They all represent the code vector polynomials. These products can be used to construct the generator matrix, which is of the order of k cross n. Let us see an example. Let us consider 7, 4 code for which g of x is given as 1 plus x cubed. Now the product polynomials can be written in the binary form up to the degree of 6 as follows. Why 6? Here see, x power k minus 1 into g of x. It will go on that way. So let us write it now. G of x is 1 plus x cubed. Now we can write it as 1, 1, 0, 1, 0, 0, 0. See, 1, 1, x squared is absent, so it is 0, x cubed is 1. Then later on, we have no term. So we will write 0, 0, 0. We will have to write 7 positions here. Next, let us take this x into g of x. X into g of x, multiply this 1 plus x cubed by x, you will get x plus x squared plus x power 4. Now you can write it as 0, 1, 1, 0, 1, 0, 0. The very first one is not there, so it is 0. Then we have 1, then we have 1, x cubed is not there, so we have 0. Then we have x power 4 is 1, then again 0, 0. Similarly, x squared into g of x is 0, 0, 1, 1, 0, 1, 0. X cubed into g of x is 0, 0, 0, 1, 1, 0, 1. Now, capital G, generator matrix, can be written in the order 4 cross 7. What was the order? K cross n. So 4 cross 7, we can write it this way. Now we have these 4 products. Each one is 7 bits. We can directly write the generator matrix. G is now, you can see here, 1, 1, 0, 1, 0, 0, 0. The first generator matrix is written. Then x into g of x product, that is written. Then x squared into g of x is written. Then x cubed into g of x is written. Now this becomes the generator matrix of the order 4 cross 7. Now therefore, generator matrix has to be in the systematic form of P and with the pipe symbol IK for the case of cyclic codes. Now this generator matrix is not containing any identity element as such. We have obtained the generator matrix, but we are supposed to have a parity matrix and a identity matrix there, which is not so. What we are supposed to do? You have studied linear algebra already to some extent, I think in M3 or M4, right? So can anyone tell me what we are supposed to do? Now to convert this generator matrix of this particular form, we want the matrix to be as a parity matrix and identity matrix. Now what we can do to have the matrix of this form? Right now it is not of this form. Right now neither identity matrix is there, parity may be there, we don't know, but identity elements are not there. What we have to do so that we will get such form? Anybody can tell me? Students do not remember linear algebra? Okay, anyway, today time is up. Think about it. In the next class, we will see. Yeah, Kuldeep is giving the answer. Last row and first row interchange. No, even if we interchange last row and first row, we will not get the identity element there. What we want is, we want the identity elements there. In the last row, you have 101. 101 is not an identity element, whereas here it is there. See, this is fine. And this is fine. 010 is fine, 100 is fine. 101 is not an identity element. That means it is not an element in the identity matrix. So that is not the answer. Anyway, you think about it, about how to convert the generator matrix into the form what we want. There are some operations which are part of linear algebra. You will have to recall whatever you learned in linear algebra. Okay, so recall and tell me in the next class. I am ending today's class. See you in the next class. Take care and bye.